So in today's lecture, we will try to see crystal systems and Bravais lattice. In our previous lecture, we had seen major points: crystallinity, that is just from the external appearance or surface nature, we cannot understand the crystallinity of a system. Crystallinity of a system is decided by the periodic arrangement of the microscopic units or atoms and molecules within the system. Or we have to use some experimental techniques like X-ray diffraction to understand this internal periodic arrangement or regularity within the system. Based on the extent of crystallinity within the system, we have come across three types: single crystalline material system, then polycrystalline system and amorphous system. In single crystalline system, this periodicity extends over a large distance, whereas in the case of polycrystalline system, we have got grains and grain boundaries, and these grain boundaries are defect regions, and which bring in the property of the system will be comparatively less if we compare the single crystalline system and polycrystalline system of the same material. Then we have come across amorphous system, which is formless, where there is no regular periodic arrangement of atoms or these microscopic units within the system. So in order to express this crystallinity within the system, the best or one important concept which we had seen is space lattice. That is, the crystal we can consider as a three-dimensional space within which there is regular arrangement of imaginary points into which we have attached bases, and then these imaginary points, that regular periodic arrangement of imaginary points, we call it point lattice or space lattice. So in the case of space lattice, we have got three-dimensional extension of these imaginary points, and these points can be expressed in terms of a translational vector T is equal to n1a plus n2b plus n3c, where this A, B and C are the translational vectors, the direction of which represent the crystallographic axis or crystallographic directions x, y and c. Or otherwise we can say this A, B and C are the smallest possible translation along three crystallographic directions x, y and z. So this n1, n2 and n3, they are just natural numbers or all numbers, and this is a very basic preliminary mathematical expression which explains or which depict the periodic arrangement of atoms or the space lattice. So this is one of the very beautiful relations which nicely present how the crystallinity is within the system. So we can, if we know one particular lattice point, we can reach any other lattice point by giving translation through this equation n1a plus n2b plus n3c. So today we try to extend this discussion to another point, that is, we have got this collection of lattice points. Many lattice points, though from any particular lattice point, if we travel along a x direction, y direction or z directions, there will be lattice points. So these lattice points are obtained by shifting it through these particular translation vector, that is, along x direction. If you move every a unit distance, there will be a lattice point. Along y direction, if you move every b unit distance, there will be a lattice point. So like that, these lattice points are arranged. So this three-dimensional distribution of lattice points. Now these three-dimensional distribution of lattice points, if we carefully analyze, we can visualize these lattice points as planes. For example, along this x direction, there will be lattice points. So these lattice points along that x direction, if we try to connect, these lattice points can be visualized as crystal planes having equal separation. So uniform separation. So for example, let us consider this room. Inside this room, so I am standing on a plane. So this room, this space can be expressed in terms of three axes. We generally take it as x, y and z directions, and one particular plane is expressed in terms of x and y plane. If x axis and y axis together we take, that will represent one plane. x-axis and z-axis taken, then we are having another plane. So, I am standing on x-z plane. So, in XZ plane it is defined or it is specified by two axes, x direction and z direction. Similarly, this XY plane, that particular plane is specified by two axes, x and y plane. So, that is we can say this XY plane can be given another name, that is Z plane. So, XZ plane can be called Y plane. Similarly, YZ plane can be called X plane. So, similarly here exactly same pattern we are following inside the crystal. So, this collection of lattice points which represent space lattice may be visualized as in another way, that is, for example, we can consider them as a set of parallel planes, that is A direction and B direction there are lattice points. So, if we take these lattice points along A and B direction from any particular lattice point, that will make a particular plane. Then just to see along that Z direction, if we use C unit upward, there is another lattice point that will also make another lattice plane. So, like that we can have a collection of parallel planes defined by the lattice vectors A and B. So, those lattice planes which are parallel and they have separation is equal to C. Similarly, if we take any the other two lattice vectors, for example, if we take A and C, then separation will be B. If we are having B and C, suppose a set of parallel planes. So, we have got planes like this and planes like this. So, one plane, if it is defined by A and B, that particular plane is called C plane. So, I call that plane as, so if it is defined by A and B, if a particular lattice plane is defined by the lattice vectors A and B, that plane can be called C. Similarly, if a particular lattice plane is defined by A and C, then that plane can be called B. And if it is defined by B and C, then that plane is called A. So, we have got the lattice planes defined by A, B, we call it C plane. C planes will be in the C direction. So, all C planes are arranged parallel and they will be moving along C direction. So, we are having these C planes, they are parallel planes having separation C unit, and B planes will have separation B unit and A planes will have separation A unit. So, if this is your x direction, then this is, we call it A, translation will be A unit. So, here in this direction we will have planes like this, and these planes are defined by B and C. We will be having those planes defined by B and C, and those B C plane, also call it A plane, they have got separation which is A. So, if we take such lattice planes, parallel planes, these lattice planes will intersect. These lattice planes will intersect along a particular line, and those lines will extend and they will intersect at a particular point, just like the corner of the room. At the corner of the room, we have got XY plane, XZ plane and YZ plane. So, these three planes, they intersect. Between two planes there is a line, and all the three planes together they meet at a point, and that point is your lattice point. So, if that lattice point, when it is given translation, it will produce the complete that is space lattice. And the peculiarity of these lattice points is that when we take this collection of these entire space lattice points, for each lattice point there is a identical surrounding. So, identical surroundings means, suppose from one particular lattice point we just observe in one direction, in any particular direction if you look at, and we will be getting a collection, some appearance will be there. Now, we move to any other lattice point in the space. If you move to any other lattice point and observe in the same direction, if you are getting the same identical appearance, then we can say that they have got identical surroundings. So, this identical surroundings around these lattice points, it is an essential requirement to be considered as periodic system. So, the periodicity is expressed in terms of testing, that is checking whether there is identical surrounding or for each lattice point, that is an essential requirement. So, let us consider a collection of these lattice planes. consider two adjacent lattice planes in a nearby vicinity. We consider two lattice planes along x direction, y direction and z direction. That is along x direction, that is we can call it A plane. So, A plane, then you have B planes and you have C planes. So, if we consider any two A plane, B plane and C plane, they will combine together to form a small space region. That small space region is a cell. So, the entire crystal, so when we consider all these crystal planes, we can assume that the complete space lattice is divided into a collection of cells, a set of cells because of these lattice planes. So, these collection of cells which are identical in structure, in shape as well as in orientation. The orientation, shape and structure of all these cells are identical, and this shape, structure or this orientation of the cells will be defined by these three lattice parameters A, B, C, and the angle between them A, B, C, and angle between them alpha, beta and gamma. So, angle between A and B is what we call it gamma. Angle between B and C is what we call it alpha, angle between A and C is what we call it beta. So, these 6 terms, these 6 parameters, they are called lattice parameters, sometimes we call it lattice constants, though it is not constant because generally this data will be varying with temperature, with pressure or maybe some addition impurities or alloying, etc. They will modify, but still we consider these parameters and they are very important, and they are called lattice constants or lattice parameters. And these lattice parameters define the shape, size and structure of this unit cell, that particular single cell which define the complete space lattice, that is called unit cell. So, lattice point is one method. So, lattice point, when it is given translation A, B and C, we will be getting complete space lattice. Now, this particular small cell unit which is given translation along A, B and C, then also we will be getting complete set of that space lattice. So, space lattice can be described with the help of the smallest unit, that particular cell, that is unit cell, which is defined by these lattice parameters A, B, C and alpha, beta and gamma. So, that shape etc. will be different depending on the magnitude of this A, B, C and alpha, beta, gamma, but actually we are interested not in the exact number, but the interrelation between this A, B, C and alpha, beta, gamma, that specify what will be the shape or structure or orientation of the unit cell. If we consider corner point, that will be a lattice point, that is the origin, and the sides of the unit cells are again this C side, B side and A side. There will be planes. The unit cell is defined by parallel planes, and therefore, it can be defined either in terms of this lattice planes or it can be defined in terms of lattice parameters A, B, C and alpha, beta, gamma. So, that specify a unit cell. So, the unit cell edge point, end point or corner point is lattice point, or each, if we take a particular unit cell, it will be a parallelepiped, because the opposite faces are parallel, they are parallelogram, and it forms a complete space, and so that altogether it makes a parallelepiped. So, in that parallelepiped, any particular corner point can be considered as origin, and the rest is defined with A, B and C. Depending on the magnitude of A, B and C, the shape or this structure or appearance will be different. So, we will be having different possible these unit cell shapes. So, a detailed study on this possible unit cell shapes are done, and these crystallographers came forward with the idea that there are 7 basic structures. There are 7 basic unit cell pattern which can be stacked to complete this space lattice, because essential requirement of unit cell is that they should be stackable. We can give different values for this A, B, C, alpha, beta, gamma, but the essential requirement is that the particular unit cell should be stackable in the 3-dimensional space to complete occupy that region. So, the corner of each parallelepiped is a lattice point, and those lattice points when given translation we get the entire space lattice, and they follow this concept of periodicity. That is, it can be defined by T is equal to n1a plus n2b plus n3c, where n1, n2 and n3 are whole numbers which specify that these points in the lattice or space lattice, they strictly follow the periodicity. That is why n1, n2 and n3 are whole numbers. And through that space lattice, suppose you are plotting a straight line. You have got collection of infinite number of points in the space, and through that space suppose you are drawing a line inside any direction, then this line will be having many lattice points on it. If we carefully analyze those lattice points, they will also have some periodic repetition. These points, lattice points coming on the line, any direction lattice points coming on the line will be having periodic regularity or order in the structure. So, that is the peculiarity of this space lattice or lattice point. So, this unit cell shape, when we analyze, we are interested in this possible that is interrelation, this alpha, beta, gamma and ABC. When we study all these possible interrelation, we come across 7 different patterns. So, we have 7 system of 7 different shapes of unit cells that will complete the space lattice, available space lattice, and they are called 7 crystal systems. So, these 7 crystal systems are triclinic, monoclinic, then orthorhombic, then tetragonal, then comes hexagonal, then rhombohedral, and cubic system. And their interrelation is, so in triclinic, A is not equal to B not equal to C, and alpha is not is equal to beta not is equal to gamma and not equal to 90 degree. And in monoclinic, A is not is equal to B not is equal to C, and alpha is equal to gamma is equal to 90 degree, and beta is not equal to 90 degree. And in orthorhombic, A is not is equal to B not is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. And in tetragonal, A is equal to B but not is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. In hexagonal, A is equal to B but not is equal to C, and alpha is equal to beta is equal to 90 degree, and gamma is equal to 120 degree. In rhombohedral, A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is not equal to 90 degree. And cubic system, A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. So, these are the 7 crystal systems. So, we can, when we consider the all possible values of A, B, C and alpha, beta and gamma, all the patterns will not be stackable, because the unit cell when defined, when we define a unit cell with the help of this alpha, beta, gamma and A, B, C, we will be getting different pattern of shapes, but the requirement is these patterns should be, or this particular unit cell shape should be stackable in 3-dimensional space. Only if it is stackable, then we will be able to give translation along A, B and C, and we will be able to that is span the complete 3-dimensional that crystal system. So, these are the 7 basic crystal systems. Now, when we analyze the possible available patterns of structures in the space or in the available in nature, it has been found that these are the basic 7 crystal systems, but in addition to the 7 basic system, that is when we try to accommodate all the available space lattice of the different material systems, we come across little modified version of these 7 crystal systems as well. So, a detailed study was done by Bravais, and in 1848 he came forward with a very valuable acceptable proposal that all the available crystals in nature can be represented in terms of 14 different lattices. These 14 lattices are basically these 7 crystal systems with little the variance of these 7 crystal systems. Maybe when we talk about cubic system, there may be few other variants. A few variants of the cubic system will also be incorporated in order to accommodate all the possible crystal that is space lattices available. So, altogether we have got 14 Bravais lattices. So, 7 crystal systems and 14 Bravais lattices. So, he has proved that there are only 14 and no more. So, with this 14 Bravais lattice, we will be able to accommodate all the available the space lattices and crystal patterns. So, there for example, let us consider cubic system. If we take a cubic system, so this is a cubic pattern where A is equal to B is equal to C. Here A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree, and all the 8 corner points, of this cube represent a lattice point. Now, if we so in a original there is space system, space lattice, these type of cubes will be stacked. So, we will have large number of cubes. So, each point, there is each corner point, there is a lattice or lattice point here, and this extent. So, here we may be having, here we will be having like that, we will be having a collection of lattice points. Now, for any particular lattice point, if you observe in one direction, you will have identical surroundings. So, it satisfies, it qualifies to be a crystal. Now, according to Bravais, so imagine you have another lattice point exactly at the center, exactly inside, well inside the center of the cube. So, we will have a collection of cubes. So, a collection of cubes extend through the infinity, that is through complete space. So, all the cubes, if you put a second additional lattice point at the center, and those lattice points, if you observe, that is, suppose you are looking from one lattice point to the complete crystal system, we can see that still it retains that concept of that identical surrounding, that is uniform translation, etc. will be possible. That means, even if there is a lattice point at the center, still it qualifies to be a crystal, or it can be considered as a space lattice, and that is a variant of the basic system, that is a cubic system. And this type of lattice system, or this type of lattice, is what we call it body centered cubic lattice. Body centered cubic lattice, so that this will also retain the requirement to be a crystal. Another variant in cubic system that we can see is, let us consider a cubic system like this. So, here all the corner points, there is a lattice point. Now, in addition to this, suppose all the 6 faces, this cube is having 6 faces, front face, back face, then top, bottom, right and left. All these 6 faces, imagine you are attaching one more point, one lattice point is attached on these each of the face. So, this particular square I am giving a center point here, this particular square I give another center point here, and this particular side I give here, and this particular side I am giving one point here. So, in addition to 8 lattice points at the corners, we have got 6 more lattice points on 6 different faces at the center. If we have a collection of these imaginary points like this, then still it will have the that particular basic requirement, that is identical surroundings and stackable unit cells. So, therefore, this also qualifies to be a crystal system, and this is another variant of the basic crystal system, that is a cubic crystal system, and this is called face centered cubic lattice. Face centered cubic lattice. So, face centered cubic lattice, body centered cubic lattice, and the simple cubic lattice where the lattice points are only at the corners. So, there are 3 variants of basic system, that is a cubic system. Similarly, tetragonal etc., they also will be having different possible variants, and correspondingly we will be getting altogether 14 Bravais lattices. So, these 14 Bravais lattices altogether they describe all the possible available crystals in nature. So, that is how we have got 14 Bravais lattices. So, there are 7 crystal systems and a few variants. Altogether we have got 14 Bravais lattices, and these variants can be represented in terms of certain letters. For example, we have P used for primitive lattice. Primitive lattice means a particular unit cell defined by A, B and C and alpha, beta, gamma, and you will have the lattice points only at the corner points. So, there are 8 corner points, there are 8 lattice points at the corners. Whereas, in the case of body centered system, a particular unit cell, if there is an additional lattice point exactly at the center of this shape, that structure, then that particular lattice is what we call it body centered system. So, in body centered system we use the letter I for body center, body centered system, P for primitive system, and F for face centered, and there is another category called base centered. Base centered means we have got, if we define a particular cubic or a unit cell, that unit cell is a parallelepiped and the opposite face are parallel, and there are 6 faces, and these opposite faces are defined by same A or B or A or C or B or C, one pair of these lattice parameters, and correspondingly they have got a name. We have already seen, that is for example, if I take this cube, so imagine this is your x direction and this is your y direction and this is your c direction, crystallographic direction. So, this distance is your A, then this distance is B, and this distance is C, translation, and this angle between A and B is gamma, angle between B and A and C is beta, and angle between B and C is alpha. So, these are the lattice parameters. This particular plane, this is a plane defined by A and C. This is a plane defined by A and C, and hence this plane is known as B plane. So, this is also a B plane. So, we will have B planes like this. This one, this particular plane, if you take this plane is defined by B and C. Therefore, this particular plane is defined by B and C. Therefore, this plane is called A plane. So, this is also an A plane. So, this is also A plane. So, naturally, the other two planes, that is one plane in the front side and one plane behind. The front side is defined by A and B. So, the front side and back side, it is C plane. So, here we have one plane here, that is C plane, other side there is C plane. So, like that many C planes. So, if there are two lattice points additional on A plane, suppose in addition to the basic that crystal system that is having a regular unit cell shape, in addition to that corner lattice point, suppose there are two lattice points on one of the faces. Suppose both A faces there are two more lattice points, still it will have the quality to be a crystal. It will that is having identical that is surroundings etc. will be satisfied, and then such a system is represented by the letter A. So, A means if it is P, it is primitive system. If it is I, it is body centered system. If it is F, it is face centered system. Similarly, there are other three types, they are called A, B and C, where A is called base centered. A, B and C are called base centered system, where base centered means along with those 8 corner lattice points, there will be 2 more lattice points on the A face. Here there will be 2 more lattice points on the B face and 2 more lattice points on the C face, and these are called base centered. And one more is there, that is called a rhombohedral system, that is represented by capital R. Rhombohedral arrangement. So, these are P, I, F, A, B, C and R, they will combine and they will form altogether there are 14 Bravais lattices. So, in this Bravais lattices we describe, or these lattice or these unit cells, we will define another term called primitive unit cell or non-primitive unit cell. So, primitive and non-primitive. So, in primitive unit cell there will be only one lattice point per cell, whereas in non-primitive unit cell there will be more than one lattice point. For example, in the case of the cubic system, so this cubic system we have, so there are 8 lattice points at 8 corners. So, if we take a simple cube, there are 8 lattice points on the 8 corners. So, these type of many cubes will be there. So, if we have a crystal a piece of solid and you just cut it, if you cut this solid into 2 halves here, suppose half of the solid is behind the board and half of the solid is in front of the board. So, if we take any particular lattice point, there will be lattice points will be like this. So, here we divide this crystal into 2 halves. So, there are 4 unit cells meeting here, they are behind the board and there are 4 unit cells in front of the board. So, here all these are lattice points. So, if I take this particular lattice point, this lattice point is shared among 1, 2, 3 and 4 unit cells behind the board and another 4 similar unit cells in front of the board. That means, this particular lattice point is part of 8 different unit cells. So, in the case of a simple primitive arrangement, so only lattice points are there only at the corner points, and each lattice point at a particular corner is part of 8 different unit cells. Because of that, out of this one unit cell, only 1/8 of its contribution will be available for this cell. Therefore, we have 8 such lattice points. For this particular unit cell, we will have 1/8 of each lattice points contribution into 8 such cells, 8 such lattice point. So, altogether you will be getting 1 lattice point in this cell. So, you will be having 1 lattice point per this unit cell. So, this is a primitive system. So, if a particular unit cell which is having lattice points only at the corners, then it will be a primitive system, primitive unit cell. Whereas, if there is a body center, if one more lattice point is here, body center, then in addition to these one, this particular one, in addition to this one, there will be one more lattice point. Therefore, body centered cubic system, there will be 2 lattice points per cell. If it is a face centered cubic system, suppose we take face center. So, if it is a face centered cubic system, here there will be one, here there will be one, here there will be one, here there will be one in front and one behind. So, there are 8 lattice points along 8 corners, they will bring 1 unit contribution. In addition, this particular lattice point is part of 2 unit cells, this unit cell and the unit cell on adjacent. So, therefore, each face lattice point, they will be shared between 2 unit cells, 2 adjacent unit cells. Therefore, only 1/2 of the total will be available for one cell. Therefore, there are 6 such faces, therefore 6 into half. So, altogether we will be getting 6 into half, that is 3, plus 1 is coming from here. So, plus 1. So, altogether 4 lattice points per unit cell in the case of FCC. In the case of face centered cubic system, there will be 4 lattice points per unit cell. So, there is an equation for that. It is total number of lattice points per cell is given by n is equal to n I. I means number of atoms inside the cell, that is the body center, plus n C by 8, because the corner, how many atoms are there at the corners, divided by 1/8, that is only 1/8 of each corner atom will be contributing, the lattice point will be contributing, and n F divided by 2, that is number of atoms in the on each face, because each face it will be shared between 2 cells. Therefore, only 1/2 of the particular lattice point will be available for that unit cell. Therefore, altogether we will be having total number of lattice points per cell can be calculated as n is equal to Ni plus Nc by 8 plus Nf by 2. So, this gives the total number of lattice point, and if this is equal to 1, this is called a primitive cell. If it is not equal to 1, it is called non-primitive cell. So, this is the initial something about our unit cells and Bravais lattice which we have seen, and more details will be discussed in our coming lecture.